You ever stop and think about how your phone, your laptop, basically every digital device you own, manages to perform these little miracles using just electricity? Well, it all boils down to a hidden language, a kind of secret code that powers our entire world. So today, let's dive in and uncover the computer's secret language, Boolean algebra. I mean, it sounds kind of crazy, doesn't it? At its very core, a computer chip is just billions of tiny little switches that are either on or off. That's it. So how in the world do we get from that simple on or off to streaming movies, playing these insane video games, and connecting with people all over the planet? That's the mystery we're going to solve. Well, the secret lies in a really special kind of language. But here's the kicker. Instead of thousands of words, this language only has two. And with just those two words, we can build entire universes. And that language is the binary system. You've probably heard of it. It's a number system with just two digits, 0 and 1. In the world of electronics, it's super simple. 0 just means off, no juice, and 1, that means on, electricity's flowing. Every single thing, every photo, every song, every line of code on your computer is just a really, really long string of these ones and zeros. Okay, so this is where things start getting cool. Look at this. If we have just two of those little switches, let's call them A and B, we can already create four totally unique situations. Both could be off, that's 0, 0. A could be off while B is on, 0, 1. A on, B off, 1, 0. Or you guessed it, both are on, 1, 1. See that? We just went from two simple states to four distinct possibilities. This is where the magic really starts. All right, so we've got our two words, our 1 and our 0. But you know, a language is more than just words, right? You need grammar. You need rules to tell you how to put those words together to make sense. And the grammar of this language, well, that's what lets a computer actually think. And that grammar has a name, Boolean algebra. It's basically the rule book that governs this whole world of on and off, of ones and zeros. It's the thing that lets a computer take those super simple binary states and start making actual logical decisions. And these rules, they're surprisingly simple. They're based on ideas you already know, like and, or, and not. You know, like if input A and input B are both on, then the output is on. Simple enough. Or if input A or input B is on, then the output is on. These little logical steps, they are the absolute fundamental building blocks of every single calculation a computer ever makes. And this points to one of the coolest tools in the entire toolbox, DeMorgan's theorem. Now, don't get hung up on the fancy name or the symbols. The idea itself is actually pretty simple. It's like a cheat code that lets us flip logic on its head. For example, it proves that saying, I do not want a burger and fries is the exact same thing as saying, I do not want a burger or I do not want fries. It's this really clever trick for rephrasing complicated problems, and when it comes to computing, that is incredibly powerful. And that brings us to maybe the most important point of all of this. The real power of Boolean algebra isn't just about creating logic, it's about refining it. It's about making our logical statements as clean and efficient as they can possibly be. I mean, it's just common sense, isn't it? You wouldn't use a long, complicated sentence when a short one says the exact same thing, would you? The same idea applies to logic circuits. We're always looking for the shortest, most direct path to the right answer. And believe me, this isn't just some abstract thought experiment. In the real world of electronics, every single piece of that logical puzzle corresponds to a physical part on a chip. So a simpler expression means fewer parts, and fewer parts means the chip is cheaper to make, it uses less power, and, this is the big one, it runs faster. Simplification pays off in big, tangible ways. Okay, so let's put this whole idea to the test. We're going to look at an actual logic circuit and use these grammar rules we've been talking about to see if we can make it better. Time for a little puzzle. So, here it is, our circuit. It takes in 5 inputs, P, Q, R, S, and T, and it runs them through all these different logic gates to spit out one final answer, Y. But here's the twist. One of these gates, one of these little components, is completely useless, totally redundant. The circuit doesn't need it at all. Our mission is to figure out which one. All right, so first things first, we have to translate this picture into a single sentence of Boolean algebra. See each of those numbered shapes?
Those are the gates, and each one performs a simple logical step. Gate 1 combines P and Q, Gate 2 combines P and R, and so on. That full equation you see written out there, that's just the mathy way of describing what the entire circuit does, from beginning to end. This is our starting point.
And now for the fun part, the magic. We take that big long sentence and we apply the rules of our grammar to simplify it. And it turns out there's a really clever little rule of logic at play here. If you look closely at the inputs for the top two gates, their combined logic already covers every single situation that the bottom gate, Gate 3, is trying to handle. Basically, Gate 3 is a backup plan for a problem that's already been solved. It's completely unnecessary, so we can just, poof, get rid of it. The logic holds up perfectly without it.
And just like that, there's our answer. Since the piece of the equation that got eliminated was the part handled by Gate 3, that gate is our useless piece. We can literally remove it from the design, and the circuit's final output, Y, will be exactly the same. We just made this circuit simpler, faster, and cheaper, all with a little bit of math.
So, okay, we found one extra gate in one little diagram. Big deal, right? Why does this really matter in the grand scheme of things? What's the big takeaway here? Oh, it means everything. The processor inside your phone, it has billions of these gates. And computer engineers use these exact same simplification techniques, just on a massive, massive scale. Every single useless gate they can find and remove helps make our chips faster, our batteries last longer, our gadgets more affordable, and our technology more reliable, because there's one less thing that can break. This little puzzle we just solved, it's a tiny window into how all modern technology is actually designed. So think about that. From just two incredibly simple states, on and off, and a handful of elegant little rules, we've built our entire digital world. It is an absolutely stunning example of how you can get incredible complexity from the simplest possible building blocks. Which kind of leaves us with one final, very exciting question. What are we going to build with them next?